kind of a new area for me because I don't normally speak specifically about nanotechnology because I describe myself as a biologist, but you'll see why it overlaps. I am really, really interested, though, in designer nanotechnology because right now, nanotechnology is hard. But to set a scale here, let me just take you into the nano world. This is the stuff we can see without magnification, really quite easily. But as we start to zoom in, we quickly exceed the resolution of our eyes. Now we need microscopes and magnification. You start to be able to see the larger cells, the paramecium, the skin cells, the human egg. It goes down way deeper, though. Much smaller cells, bacteria, mitochondria and organelle, and then into the world of viruses. Now you're getting into the nanoscale, and ultimately into the subcellular components that allow cellular life to work and operate. This is an unfamiliar world to most people. Out of sight, out of mind. It is as hard to grasp for most people as data or the future in other invisible things. When you see an image like this about nanotechnology, it's just fantasy. When you get down to the level of the molecules, everything is dynamic, everything is molecular. There are no smooth lines. This is an animation called cell pack. It essentially gives a sense of what these molecules are doing down at that scale because they're so small. Just the ambient energy of heat makes everything move. It's like Brownian motion. Everything is constantly, dynamically interacting with each other. Another animation by Janet Iwasa kind of shows some of the complexity of this. This is just how micelles form to essentially make simple cell walls. All of this has to be simulated and done with computers because the physics down at this scale are completely unlike any of the physics in everyday life. It's completely unfamiliar and done at timescales that are bizarre to us. So I kind of cheat. Tom Knight, a synthetic biologist at MIT, says biology is the nanotechnology that works. And it is. We are all made from nanotechnology. Nanotechnology is the dominant force on this planet in living systems. It's been that way for billions of years. And the cool thing is, all the nanotechnology uses cells. Cells are the foundation of all living things, as you know, but I look at cells just as a type of computing and manufacturing hardware that self-assembles. And it has a programming language, DNA. And this is universal across all living things. So if you're really interested in nanotechnology, but want to do it digitally and do it in a way that scales and that you can share the code, you really have to think about programming living cells to do the work and using DNA to do it. So as Daniel said, I used to be with faculty full-time at Singularity University. Autodesk was one of the founding sponsors of Singularity University. It was my introduction to the company, apart from some friends that worked with Autodesk Research in Toronto. Autodesk makes software for designing most of the things in the real world around us. It's actually a fairly old software company. But I had no idea the range of things that it did. It has over 8,000 employees, and almost nothing in the world gets made today that isn't touched by the software in some way. You just got a really great overview of 3D printing, but manufacturing in all forms really takes some sort of specialized software. For me in particular, this was fascinating because I noticed that the company didn't have any design software for the two things that really interested me: nanoscale systems and self-assembling living systems. And I challenged them on it. And they said, let's explore this. And so in 2012, they formed the BioNano group. Now, for the people who are not familiar with Autodesk in general, the software touches the world in a lot of different places. Most of the time, it reaches us through movies and entertainment and advertising, because we make it possible for people to visualize things that simply don't exist yet. Or you can't get a holistic view just through through one individual. Things like airplanes have millions of parts that all have to come together seamlessly to make the final device. It can only be done in software. So I'm always learning on this job. We're pushing the limits now with our Pier 9 facility. We have fun, it's filled with artists. And today there's a really tight coupling between design and manufacturing because of what you just heard. The printers are becoming extremely cheap and they're all digital. And we're seeing a massive shift now from just professionals using digital design and manufacturing to basically everyone. It's gone consumer, it's gone to kids in school. So we're kind of a bizarre software company because we actually have a functioning biolab that we use for prototyping. This was kind of a big deal when we set it up because it was just so strange for us. But it's well outfitted, and I have a team now. They're pretty incredible. It's about 20 people. Half of them are scientists with domain specialties, and half of them are computer programmers that don't necessarily write all the code, but they take the code that we've been developing for other areas of design, and we port it and use it for bio-nano applications. The job of the group really is to take computer-aided design and computer-aided manufacturing and our experience in that area and move it into the bio-nano domain, which for the most part has been done by individuals or small groups or proprietary companies in a very artisanal way. So I look at it as really as just software and printers. And if you look at it as, these are some of the printers that are available to us today. The 2D printer, okay, you write papers, but actually you can lay down a lot of stuff in 2D printers. You can now 2D print electronic circuits just with conductive ink. So we're finding all new ways to use that. We have a lot of areas in 3D printing, some of which was discussed in the last talk, so I won't go into the overlaps. And bioprinters for sure are really cool because cells are actually fairly large devices. You can just print them and position them in space very easily now. But the real nanoprinter that I use every day is the DNA synthesizer. It is a printer that prints the DNA molecule, chemical bit by chemical bit by chemical bit, and strings it together to write code. It's really the only printer that I'm interested in for the most part because it's really the only chemical printer you can have sitting on a desk that can do so many different things because it can reprogram the cell, which is essentially a 3D printer for millions of chemicals, all in one go. Anyone that's ever worked in a chemistry lab before knows it can be exciting sometimes because things tend to explode or catch on fire or anyway. The other area that I think is fascinating is robotic labs, because if you really want to get exponentials, you got to get people out of the loop. We're not exponential, except growing from a baby to an adult, perhaps. But let's face it, we can't go exponential. We work 8 hours a day. The DNA printer technology that we have today is not very good, though. I've been tracking this technology for 15 years. When you could write 1,000 base pairs of code, you could make a gene. You could make a single protein then. Or you might be able to make, again, some peptides. You just heard from Moderna Therapeutics. This is really powerful because if you can write short strings of information, you can start to change the way cells behave. When you get up into the 10,000 base pair range, you can actually start writing small genomes, things like viruses. That's a fair amount of code. It's actually about 10 genes strung together, so you can do a lot of metabolism. And between 10K and 100K, you do metabolic engineering. And there's a lot of people working on that today, reprogramming cells to do really useful things. I think you'll hear some of that about in the next session. But the reason why I stay clear from that right now is because I want to be able to digitally design and print, and I want what I print to represent what I designed. And right now, we cannot design cells well enough that we actually know what we're going to get. And everything beyond this, bacteria, yeast, chromosomes, eventually human genomes, that'll come as DNA synthesis gets better. And it will get better. It's been growing exponentially. So right now, I'm focusing all of my attention on nanoparticles. Nanoparticles are what they sound like. They're particles at a nanoscale. typically under 100 nanometers. My favorite one, to do that, first of all, since you can't see these things and you don't really have a great sense of them and they're hard to manipulate, we've been taking some of our software tools for other industries and we've been bringing them down so that they work with molecular systems. This is software that's available today. We've been opening it up for the developing community. It's not something that you're going to use at the moment, but what is really fascinating, this is one of the most powerful molecular viewers available today. And because we've got a lot of experience with the cloud, et cetera, you can do really high-resolution models just over a web browser. This is really kind of mind-blowing technology on the back end. This is kind of an example of what it looks like. Here's a component from a virus. You can blow the protein components apart. It's kind of like a little molecular jigsaw puzzle. That's kind of cool, so I'm just exploding it. Now I'm going in and I'm saying, show me the atomic resolution of that particular thing, and you can zoom right in to the specific molecule. And again, you can manipulate all of this as well. I'm just giving you a quick visual tour. When I pull back out, now I want to assemble the whole virus particle. So here I'm just going to click on that. Now it has to go and build the rest of the virus capsid from those components. It takes a few seconds over a web page, and I was just doing this in my hotel room. But this is what you end up getting. So now you have the full assembled virus capsid. Inside would be the viral DNA that actually has the full program. Again, you can explode it out. You can compress it back in. You can cut it and slice it so you could actually look inside. Now we're starting to build the DNA visualization tool so you'll be able to see the DNA inside this virus capsid. You can also take atomic coordinates as well, get the distance between any 2 points. And this particular viewer has all of the features that you need for VR support. So you can go in using an Oculus or any of these types of systems, and essentially multi-user support. So you'd be able to do this with friends and colleagues around the world. Of course, it's pretty easy to go and 3D print that model. This is Daisy Rosario from Mike.com, who came out to interview me a few weeks ago. But just holding a physical model of a virus in your hand makes that nanoparticle real. Because now you get a sense of how this thing, what it looks like. It's never unfamiliar again. Once you see a flu virus, or in this case, it's a bacteriophage, it's just a virus that infects bacteria, you never forget it. You're friends for life. And of course, you can have it sitting on your desk, too. But we can make the real virus. Using the same tools and technologies, we send the digital DNA design file, again, it's just code on a computer, to a company like Gen9. This is a 3D print shop for DNA. Not the only one in the Bay Area. There's another company called Twist. There's DNA 2.0. These are just printers. They're like Kinkos for DNA. They're really good. And in a few weeks, they'll print your DNA. Actually, it's getting faster. In about a week to 2 weeks, they'll turn around and they'll print your DNA, and then you can actually turn it into the real particle. And last year, I made Autodesk's first synthetic organism. This is just a growth plate, a bacterial growth plate, E. coli background, but wherever you see a spot, that's where a synthetically constructed genome for this phage infected an E. coli cell and started the chain reaction of making more phage and killing more E. coli cells. It only cost $1,000 to make this synthetic virus, and it took about 2 weeks. So nanoparticle engineering is already pretty cheap and powerful, and it's only getting cheaper. For the last year, my team and I have been prototyping doing virus production, end-to-end, all digitally, using work cells like this. This is a company called Transcriptic in Menlo Park. It's created by a young CEO that just said, I never want to work at a lab bench because it's too slow, you get bad data, you forget things, there's really bad reproducibility. So they made a robotic lab. It's all the same equipment you'd have in a lab, but now there's a robot that does all of the routines. And it works really well. Now, it's the size of a shipping container, but it's completely accessible online. This is a cloud laboratory, and if there's one thing you'll learn about exponentials, is things get smaller, faster, better, cheaper. So once you've got a robotic lab, you know it's going to get smaller. Eventually, this will be a box on your desk. Eventually, it'll be a brick. Eventually, it'll be a chip. We were really pleased with our work on this, in the fact that we were able to completely make these particles without a human hand touching it. And we were able to do all the growth curves, we were able to do the plaque assays. Was it easy? Will it scale in this form? No. But we've shown that digital paths are possible, and now the software is what links it all together. Already, I'm going now to applications. My project for this year is to start working with veterinary oncologists to start making oncolytic viruses for dogs. Working with them to do the design and manufacturing. And the beautiful part about this is you're essentially 3D printing viruses that give cancer cells a cold. And it's so cheap to do it, you can do it for one dog at a time. So I'm not the type who wants to go and fight with the FDA, and I work for a software company. I don't want to worry about, all I want to do is make things faster, better, cheaper. But working with the dogs is a really good thing because the owners ultimately are the HMOs, the payers. And really, I can tell you, if you get a video of you working with dogs, it gets 1 million hits. I'm really thankful for Mike.com and featuring some of this early stage work. And I think it's going to be some of the most exciting work at the leading edge of oncology. I think the dogs will lead the way for humans. Now I want to switch gears and talk about a non-biological nanoparticle. This is DNA origami. Now it's using DNA again, but as a structural material, not a programming language. And that's because we understand the physics of the DNA molecule really well, and it's an information encoding polymer, so we can change the information. And this was from a 2006 paper by Paul Rothman, who won a MacArthur Genius Award. But here he's using he's taking a long string of DNA and he's bending it and folding it in different ways. And the happy face for me just works, because if you can make a happy face out of DNA and look at it with atomic force microscopy, that doesn't scare anyone. I can tell you, even harmless viruses scare people, but this does not scare anyone. I like that. And since then, this technology has evolved extremely quickly. Now, through using computer algorithms, we can make virtually any 3D shape. This is not my work. This is a recent paper that just shows you can design almost any shape imaginable, including a Coke bottle, apparently, and a Stanford bunny. And the computer will figure out the design. It'll self-assemble into that shape. Now, these are not functional nanoparticles, but we've already done collaborations with folks like Sean Douglas who have functionalized them. So this is a clamshell nanorobot, and it really is a nanorobot. It has a little lock and key system, and the purple things in the center are a cytotoxic protein. But when it binds to the right receptor on a cell, it opens up like a clamshell phone. Those proteins are now biologically active. It kills the cell. It works great in a dish. Other pharma companies are starting to develop this technology as a possible therapeutic. But again, the point that I'm trying to make is it's just digitally designed and manufactured. So it's kind of in the same line as Moderna Therapeutics or 3D printed nanostructures. We've demonstrated we can do this even with a small team. This was from a 24-year-old colleague of mine. He said, I'll just take the Autodesk logo, do it in DNA, and turned it around and imaged it a few weeks ago. And again, this is 100 micrometers. The logo self-assembled perfectly. This was just done for a few $100s worth of synthetic DNA. This was the first time. You can see all the A's in the upper corner. This is amazing stuff. And just as your kids today might be learning about 3D printing, they'll be able to 3D print molecules. This is not expensive. And I recently learned, and this is from a 2013 paper, but now people are doing protein origami as well. And the last time I checked, protein origami was pretty much how all of biology gets made. So this is going to advance quite quickly. But where I think it gets really exciting, is the intersection of nanoelectronics and biology. Because I can tell you, biologists are not the folks that have been thinking and visualizing and being empathic with molecules very much. They're just not. We all tend to think about and focus on the things we see around us every day. But the people that really do think at the nanoscale and empathize with the nanoscale well are the folks working in the electronics industry, because they've been working at that scale every day for over a decade now. Now, there is an intersection that really touches on my world, and it's the latest generation of DNA sequencers. This is a DNA nanopore sequencer, or at least an illustration of how they work. There is essentially a pore. DNA, single strand, goes through that pore, and as it does that, it disrupts the flow of current, basically shown by the black dots here. And electronics are so sensitive now, you can actually read the difference of DNA bases in the changes in current flow. This allows you to do really rapid, really cheap, long-chain DNA sequencing. This is the state of the art in microfluidic chips in my field. This is a chip that was published this last summer by the Joint Bioenergy Institute out in Emeryville. And it will essentially do genetic constructs on a chip. I can tell you the technology here is laughable compared to a 7 nanometer processor circuit. So things have to change in biology. We need much more investment to really start driving the field exponentially. But that's starting to happen. This is Fab 8, Global Foundries, one of the largest chip fabs in the world. It was the biggest foreign investment on US soil, I believe, a few years back. It's in upstate New York. This is where some of the most sophisticated electronic chips in the world are manufactured. But they realize we're at the end of Moore's Law now. Basically, in 2D, they've kind of maxed it out. They might space it out in 3D, but you can only shrink a circuit so far. And in fact, below 5 nanometers, only life knows how to position molecules with enough accuracy to build bottom up. So groups like Global Foundries are starting to invest and learn about the mechanisms of life. And as they do, they'll start to make equipment like those nanopore sequencers. They'll make sensors, or they'll turn it around and they'll start making electronically controlled polymerases to write DNA cheaper than you could ever imagine, or use DNA as a storage medium, on and on and on. I think we are entering one of the most exciting and explosive growth periods in biology that anyone has ever seen. It will take a decade for this to really hit the knee of the curve, but the exponentials are clear and the benefits to your field immense. Thank you.
Thank you. One question. So you have previous work with something called Pink Army, where you're envisioning sort of programming viruses for particular cancer therapies. Does that sort of blend in this area? You think in 10 years we'll be at the level of doing digital origami for personalized viruses?
So you hit my core motivation. I worked with Amgen for 7 years, and what I learned from Amgen was that drug development was not an exponential. So I looked for a way that I could make N of 1 medicines, because when you make a medicine for one person, you kind of wipe out the need for big clinical trials, and that's where I saw the exponential possibilities. Pink Army was the first open source biotech company really focused on making N of 1 cancer therapeutics. What I learned, though, was we have to go build the tools, and Autodesk builds tools to help people design the world. It was a great fit. Pink Army still exists. It'll probably end up being open source, and crowdsourcing has evolved quite a bit since I first founded it. But once these tools are out there, and they're happening every day, they'll be available for everyone.
And one of your great quotes is, viruses are the apps for the body.
They are. Actually, the apps for the ecosystem. Viruses are what allow genetic code to move between species and through the world. That's why we all use a standard genetic code.
Great. Thanks, Andrew.
Thank you.
Cheers. All right.